Welcome to Maths with EJD. I've been talking about numerical analysis, and this is the third video I'll be doing on nonlinear root finding methods. I've talked about bisection, I've talked about seconds. Of course, that's after talking about the preliminaries like error analysis, approximations, and things like that. So generally speaking, for nonlinear root finding, so we have two broad classifications. We have two broad classifications. One of it is 2-point. We have 2-point methods, and we have 1-point methods. So the idea of 2-point methods, for instance, is that you have you have an interval within which the solution lies, or you have two initial guesses. And the examples on that is bisection, which requires an interval that you keep having until you find your result within it. So you have the second method, and then under 1-point method, we have fixed point iteration, and then we also have Newton-Raphson method. So these are 1-point methods. So these ones require just one initial guess. So far we've done bisection, we've done second. Now we are going to look at fixed point iteration. That's the essence of this now. Fixed point iteration method. Okay, now the fixed point iteration method is based on transforming the equation, whatever equation you're given, transform the equation into an equivalent form, x equals g of x. This is like the key part of this. X equals g of x. All right. So this allows iteration over successive guesses, approaching the solution. Now, the convergence of this method depends on the function's properties. So it means when you have a given function f of x equals 0, you can write it in different forms, x equals g of x. So the property of those functions will now determine if you are going to have convergence or not. So let's look at the steps we need to follow to implement the steps in fixed point iteration. Okay. So the first step is to rearrange the equation f of x equals 0 into the form x equals g of x. That's a key part, like I keep saying. Then 2, choose an initial guess. So it can be anything. You can choose whatever, but your initial guess is going to determine how fast your solution converges or whether it will diverge. 3, then you can now apply the iteration formula. It's called fixed point iteration. Apply the iteration formula xn plus 1 equals g of xn. Okay, that's the iteration formula. Of course, as you can see, this is based on what we would have done here. Then finally, the stopping criteria. How do you know when to stop? So what you do is you repeat until absolute value of xn plus 1 minus xn is less than a tolerance limit that you're given. All right. So epsilon is tolerance limit or level, as you may call it, tolerance level. So, I mean, the smaller the tolerance limit, the more accurate your result. Xn plus 1. Okay. So now you discover that so far we've had like two kinds of stopping criteria. It's either you compare the successive iterations or you check the function. So it could also be something like absolute value of f of x n plus 1 at any point in time, that it must be less than the epsilon, the tolerance level. Okay, so with that said, can we then take an example? In fact, the same example I've been solving with bisection, secant, that it's the same example I like us to tackle right here. Okay, so let's take the problem example. Find the roots of f of x equals x cubed, same question, minus x minus 2 equals 0. Given initial guess, x naught equals 1, and tolerance limit epsilon equals same tolerance limit 0.01. Because at the end of the day, we want to be able to compare these methods and see which one does better. So I mean, the initial guess x naught equals 1. If you're not given the initial guess, you have to guess yourself, right? You better pray that you guess something as close as possible. But I mean, any guess, you can guess 1 million, you can guess 5,000, but it's better to guess. I mean, if you look at the way the situation, this equation is, you can already have an idea around where the solution is going to be. So because your guess will determine how fast your iterations will be, or how many iterations you have to make before you get your result. So that's the example there. Okay, so let's go on because um we are going to have all the possible expressions for that we can have. So you have f of x equals x cubed minus x minus 2 equals 0. Then we have initial guess x naught equals 1, and then we have tolerance value 0.01. Okay, now so what do we do? If you consider the expression, considering x cubed minus x minus 2 equals 0. So look at the possibilities you can have. This can actually be expressed as x cubed minus 2 equals x. That's okay. Or let me just start from the beginning so I can do every step. So x cubed minus x minus 2 equals 0. So you can transfer x to the other side, right? So you have x cubed minus 2 equals x. So at the end of the day, you can say x is equal to x cubed minus 2. So based on this now, you can have x n plus 1 equals, so this is more like your xg of x. So this is like your x equals g of x that we've been talking about. So you can now express it as a formula, which is now xn plus 1 equals xn cubed minus 2. So this is an expression you can use for your iterations. So that's one way to express the situation. So then another thing you can have is this. You can also have so this same expression now. This same expression, you can have it as x cubed minus x minus 2 equals 0, such that you now have so you have x cubed equals x plus 2. That means minus x goes here, minus 2 also goes here. So you have x cubed equals x plus 2, so that at the end of the day, x is equal to cube root of x plus 2. I mean, what that means is that x is equal to x plus 2 raised to power 1 over 3. So we can also have that. So this is the form x equals g of x. But then we can write it, okay, this is the form x equals g of x. But then we can still write it as the formula it should be. That would now be xn plus 1 equals xn plus 2 raised by 1 over 3. So we have that. So that's another possible way to write that. Okay, but I mean that's not all. We can still write it. We can still write it as this. You have x cubed. You have x cubed minus x minus 2 equals 0. So we can be ingenious about it, and we have x cubed equals x plus 2, and then we can now divide through by x squared. So we have x cubed divided by x squared equals x plus 2 divided by x squared, okay? So that at the end of the day, we have just x here equals x plus 2 divided by x squared. So this form again is the form x equals g of x. That's another one. And then we can write the formula at the end of the day to be xn plus 1 equals xn plus 2 divided by xn squared. So again, we have this formula here, and then we have this here. So we have three possible ways of expressing the same thing. So now we want to see which of these ones will give us the best results. Okay. So now let the iterations start. Okay. So let's start with the first one. So for this now, don't forget our function is we have f of x equals x cubed minus x. Oh no, we are good now. We are good now. All we just need would be the so if you want to go for the first iteration, this is when n is equal to 0, it means x1 is equal to x naught cube minus 2. And don't forget what x naught is. X naught is 1, right? Yeah, x naught is 1. So we can just substitute that. So we have x1 equals 1 cube minus 2. So that is x1 equals 1 minus 2, which is minus 2, which is minus 1. Yes, that's minus 1. So we have our first result for this. That is x1 is minus 1. Or let me make it neater. So x1 is equal to minus 1. That is our first result after first iteration. Now, so let's check. Is this good enough? Absolute value of x1 minus x naught is actually equal to absolute value of x1 is minus 1, x naught is 1. So that's minus 1 minus 1. And that's okay. Let me be clear enough. This is absolute value of minus 2, which is 2, and that is greater than 0.01. So this is not, we can't stop here yet. Okay, so that's one iteration right there. What if we go ahead and now do the next one? So we now have x2 equals x1 cube minus 2. Okay, so that means that x2 is equal to x1. The x1 we got was minus 1. So that is minus 1 raised to power 3 minus 2. That is minus 1 raised to power 3 is minus 1 minus 2. And that is minus 3. Okay. So it means that we have x2 to be minus 3. Another solution right there. Okay. So again, let's check. Have we arrived yet? So to check for that, we have absolute value of x2 minus x1. That is absolute value of x2 is minus 3. x1 is minus 1. So that's minus minus 1. And then we have absolute value of minus 2. And that's, minus 3 plus 1 is minus 2. So that is still 2. Absolute value of that is 2, which is still greater than 0.01. So iteration continues, right? So iteration continues. So again, we keep going. So now we need to go for x3. So x3 now is equal to x2 raised to power 3 minus 1, minus 2, right? Minus 2. So don't forget, everything we are doing is based on this formula now, this form of the expression, and it is derived from the original equation. So now we have x3 equals x2 cube. X2 is minus 3, yeah? Yeah, x2 is minus 3 from here. So that's minus 3 raised to power 3 minus 2. So x3 is equal to minus 27 minus 2. So x3 now is minus 29. Yeah, that's minus 29. So that's x3. Okay. Now, is that a good enough answer? So absolute value of x3 minus x2, that is absolute value of minus 29 minus x2 is minus 3, minus 3. So that is absolute value of minus 26. So again, absolute value of minus 26 is 26. 26 is greater than 0.01. In fact, it will look like this one is diverging. Okay? To look like this one is diverging. So what do we do? So since it's not even converging, let's resort to Python code. Let's resort to Python code later. Okay? So it's not giving us any sign that it's going to converge. So it means that expression is a bad is bad market, like they say. So this one is not looking like it's going to give us anything tangible. So let's move on to the next one. So for this next one now, so here for the first iteration, we have x1. When n is 0, we have x1 equals x naught plus 2 raised by 1 over 3. Thankfully, x naught is, x naught is equal to 1. That's from up here, x naught is 1. So that means x1 is equal to 1 plus 2 raised by 1 over 3. So that x1 is equal to cube root of 3. And cube root of 3 is, that's, what's that now? Okay, 1.442250. Okay, so that's x1. I mean, this is looking hopeful. This is looking like it's making sense. So let's check absolute value of x1 minus x naught is equal to absolute value of 1.442250. X naught is 1, so that is 0.442250. Of course, this is still greater. This is greater than 0.01. So iteration continues. Iteration continues. Okay. So, but I mean, the value is very small. It's not like the first one I was giving us 2 and all those big numbers. Now we move on to the next iteration where we go for x2. So x2 now is equal to x1 plus 2 raised to power 1 over 3. That's cube root of x1 plus 2. Now x1 is 1.442250. So x2 is equal to 1.442250 plus 2 raised by 1 over 3. So x2 is equal to 3.442250 raised by 1 over 3. So we have x2 to be, x2 now is 1.509898. So we have x2 right there. So we can then check for the convergence. So absolute value of x2 minus x1 is equal to x2 minus x1. So our x2 now, okay, let me take it down. So this is absolute value of x2 is 1.509898 minus x1, which was 1.442250. So that's equal to 0.0674. 648. Now this is looking hopeful. At least it's getting reduced, although this is still greater than epsilon, but we are good. I mean, it's looking like a good on the right track, right, with this one. So, but then we have not arrived. So iteration still continues. Iteration continues. So now we can go for x3. So x3 is equal to x2 plus 2 raised to power 1 over 3, right? Yeah, that's it. So x3 now is equal to x2. x2 here is 1.509898 plus 2 raised to power 1 over 3. So that means that x3 is equal to 3.509898 raised to power 1 over 3. So that x3 is equal to 1.519724. So that is x3 right there. Okay, so let's check to see if we have arrived or not. So we have absolute value of x3 minus x2, and that is equal to absolute value of 1.519724, which we just got, minus 1.509898. So that is equal to 0.009826. As small as, no matter how small, it is still less than epsilon. So what do? We can say solution obtained. So, and that solution is going to be x3. So we can now say, therefore, x is equal to x3, which is 1.519724. Okay, that's the solution to the problem as far as this expression is concerned. Okay, so but then we still have another one. So our deal is now with this one, we did 3 iterations and we couldn't get any tangible result for the first one. For the second one, we have got a result, but I mean, is the next one going to perform better than it? That's the question now. So then we go for the third method, right? And that is here now. So first iteration is going to be x1 equals x naught plus 2 all over x naught squared. So don't forget x naught is equal to 1. So x1 is equal to 1 plus 2 divided by 1 squared. So x1 is equal to 3. 3 in short, x1 is equal to 3. So absolute value, so we test absolute value of x1 minus x naught is equal to absolute value of 3 minus 1. Okay, and that is simply 2, which is greater than epsilon. So iteration continues. Iteration continues. But this one is not looking, it's not looking like there's hope. But let's still keep going. Let's do at least 3 iterations and see what happens. So again, we go again and we have x2. x2 now is equal to x1 plus 2 raised to power x1 squared, okay, based on this original expression here. All right, so what does that tell us? So it tells us that x2 is equal to x1 is 3, okay, x1 is 3 from here. So x1 is 3 plus 2 divided by 3 squared. So that means x2 is equal to 5 over 9. So x2, I mean, you can leave it as 5 over 9, but it's 5 over 9 is also 0.555556. So this is x2. That's 6 there. So then we check again. Are we there yet? Are we there yet? So absolute value of x2 minus x1, that is equal to absolute value of 0.555556 minus 3. That is equal to, I mean, it's 2.44444, but the absolute minus 2.4444. So the absolute value is 2.444444. And this is still greater than epsilon. So it's not looking like there's any hope in sight yet. So iteration continues. Iteration continues. Okay, so we go again for the next one, which is x3. So again, we know x3 would be x2 plus 2 all over x2 squared. Okay, so that is x3 equals x2. Of course, we already know that's 5 over 9, or 0. That's 0.55556 plus 2 all over 5 over 9 squared. 5 over 9 squared. So if you do all of this, you're going to get 8.28, 8.28000 if you like. So it's basically 8.28. So that's x3. So I mean, have we arrived? Let's see if we have arrived. So to do that, we check absolute value of x3 minus x2. So which is absolute value of x3 is 8.28. 8.28, 1, 2, 3, 4, minus 0.555556. Okay. And that is equal to 8.130055. Now, this is bad sign, right? This is still greater than epsilon. And to make things worse, it's not even reducing. So it's just the value is just increasing. So I mean, it means we shouldn't even bother ourselves further. Let's just resort to Python code. But it's already obvious that this will likely okay, well, so far we are saying that this is okay, no, this is diverging. This is diverging. So we'll look at the Python code to confirm, but the possibility is that this is going to diverge and this is going to converge. I mean, this has, in fact, we're able to get a result, because a solution was obtained. So this this diverges, this converges, and this also the last one diverges. Okay, this diverges. So only the one in the middle seem to be the one with the cube roots seem to be doing well. So let's look at the Python code for this. Um, let's look at the Python code for that. Yeah, this is fixed point iteration, right? Yeah, this is a fixed point iteration. Now you see, I mean, the whole thing is defined, view, line, show line numbers, right? So I mean, the whole thing is defined, so you can study it to see what the whole thing is about. The tolerance limit is 0.01. That is fixed here. The maximum iteration is 1,000, so it can go beyond, it can go as far as possible. And then for the first expression, which is x cubed minus 2, based on the breakdown, we got this. So if you run this now, from what we did there, we saw that it was diverging, right? And by the way, you can see the value are so big that it's even giving an error. It says integer too large to convert to float. So you can see the number is going so fast, very big. So so that confirms the fact that it is diverging. Okay. So for the second one, if you just look at line 19, this is where we talk about cube root of x plus 2. So in this case now, if you run this, yeah, this is behaving well. I mean, in 3 or 4 iterations, we're able to get a result. So this is looking good. So total iterations 4, and we're able to get 1.52. I think we got 519 something. So there's a bit of difference, because of all those approximations in the process. So you can see this one is giving, second one gave us a good answer, the one with cube root of x plus 2. Then the last one, which is x plus 2 over x squared, you can see this one, of course, we suspected that it's going to diverge. And for sure, the result is too large. So you can see the results started increasing 1, 3, just like what we got, 0.5666 and 8.28 and so on. And then all of a sudden becoming extremely large. So you can see that only the second one, the one in the middle, is looking good enough. So only this expression of xg of x is working. Okay, so the other two are diverging. So normally, if 3 of them are converging, then you now choose the one that requires the least number of iterations. That's what you now consider. All right, so with this, we come to the end of fixed point iteration. It's really interesting. So you get your expression, change it to something like x equals g of x, and then do your iterations and see which one converges. So here only one converges. So it means that we are only going to settle for this result right here. If all of them are converging, so you are going to now choose the one that converges faster, the one that requires least number of iterations. In the next video, I'll be talking about Newton-Raphson method, which is another 2-point method like fixed point iteration, and we'll see how how that compares with all the ones we have done. So if you have not subscribed, if you have subscribed to the channel, thank you. If you have not, please go ahead and do that right now. Hit the notification bell so you can always get alerted each time a new video is released. Then comment, let me know if how helpful these videos are for you. Let me also know if there's a problem you like me to solve, a topic you like me to teach. And lastly, like and share so that more people can have access to this great content. Like, come your way again. Keep doing much right. Bye.